Hello everyone, I welcome you all in lecture 7 of module 2, that is axial force diagram, shear force diagram and bending moment diagram in beams under course mechanics of solids. And today we will be discussing about the relationships between load, shear force and bending moment. Actually in earlier lecture this relation was discussed in detail, but still we will be discussing a little bit about it. So this is a part of beam, and let us say at a particular section the value of shear force is F and the value of bending moment is M, and say it is at distance x from origin, and after dx distance apart, if we consider another section, as shear force value or bending moment value is changing from point to point over the length of that particular beam, then say after dx distance apart, if we consider another section, the value of shear force is F plus df. It may be increase in the value or decrease in the value. Similarly, M at that particular section, let us say it is M plus d. So we have discussed in the earlier lecture that the rate of change of shear force or slope of the shear force curve is equal to the intensity of the loading, and the relation was something like this: W is equal to df by dx, and that was rate of change of the shear force. In addition to that, we have discussed that the rate of change of bending moment is equal to the shear force. So that is F is equal to dm by dx. So dm by dx is rate of change of bending moment, and that is equal to the shear force at in between those two points. So with these two relations, df by dx is equal to W and dm by dx is equal to F, that is shear force. So we can write that d2m by dx square is df by dx, and that will be intensity of the loading. So in addition to that, what we discussed earlier is at a point where dm by dx is 0, then at that point shear force is 0, and it is giving us the point at which the value of bending moment will be maximum. And we also discussed earlier that the point of 0 bending moment, where the type of bending is changing, it may be earlier sagging, it is changing to hugging bending moment or hugging to sagging bending moment. So that is called as point of inflection or point of contraflexure. So that also we have discussed earlier. The variation of shear force between two sections is the area under the load distribution diagram. So we have discussed that Fa minus Fb is integral W over dx, and also the variation of bending moment between two sections is equal to the area under the shear force diagram. So that is Ma minus Mb gives integral F dx. Okay. So these different equations we have discussed earlier, and theoretical part we have discussed earlier, which is giving us relationship between load, shear force and bending moment over the length of the beam. So in relation with this, we will be going for further numerical, and the numerical is something like this. A shear force diagram of a simply supported beam is as shown in the figure. Find the force acting on the beam. So what earlier in all numerical, the beam and the loading acting on it was given, and it was asked to analyze that particular beam to develop shear force diagram and bending moment diagram. Now in this particular numerical, shear force diagram itself is given, and then you have to develop how the beam is and how the loading is acting on that particular beam, and then from that you again need to go for analysis for bending moment, and then you need to develop bending moment diagram. So that kind of analysis we are going to do in this particular numerical. The diagram given for the numerical is something as shown in figure 13a. So there are 4 different points A, B, C and D. At A, shear force value is 95 kN, and at C, shear force value is 9 kN, and it is negative, and the distance between A to C is 4 meter. Distance between C to D is 2 meter, and at D the shear force is 77 kN, and at B shear force is 77 kilonewton and both are negative, and distance between D to B, it is given as 2 meter. So we'll go for solution of this. Now, as at point A, shear force is 95 kilonewton and positive at point A. So this is from 0 up to 95. So it means there must be upward reaction or upward force, and that itself says that at A there must be a support. So vertically upward reaction or force must be acting over there, and magnitude of that is 95 kilonewton. If we go further from A up to C, then the SFD shear force diagram is inclined. Thus, this position must be subjected to uniformly distributed load. So, if there is uniformly distributed load in between A to C, meaning of that is due to UDL, there is inclined variation of shear force, and as in SFD it is given that this is inclined from 95 kilonewton positive to 9 kilonewton negative. Okay, so it says that there is UDL acting in between A to C, and the magnitude of UDL will be W is equal to dF by dx. This we have already discussed. So W can be calculated as 95 minus 9. So it is again going to minus. So it should be plus. From 95 it is going to 95 plus 9, and that is 104 divided by 4. It is over length 4. So it is divided by 4. That gives us 26 kilonewton per meter UDL from point A up to point C. Now, if we go further, in between point C and point D, from point C up to point D, the shear force diagram is horizontal. So it shows that there is no force in between C and D. In between C and D, there is no other force acting. And then at D, at this point, the one magnitude is 9 kilonewton and another magnitude is 77 kilonewton. So there exists a vertically downward point load equal to 77 minus 9. Again, it is from minus 9, it is going to minus 77. So force value will be 77 minus 9, and that will be 68 kilonewton. So further, again in between point D up to point B, variation of shear force is not existing. So that is horizontal. So there is no force acting in between D to B, and then the point B is other support, and reaction at support, that support B is 77 kilonewton. That is the meaning of that. So the beam and load distribution diagram then can be drawn something like this. So what we have is, this is 95 kilonewton shear force at that particular point. So that is the force, or that is the reaction at A, and in between A to C, the variation of shear force is inclined. So there is UDL in between, and magnitude of that is 26 kilonewton per meter, what we have calculated earlier. And at D, again from 9 kilonewton shear force is suddenly increasing to 77 kilonewton. So difference of these two is 68 kilonewton point load acting at D, and at B there is 77 kilonewton force and nothing is there. So that must be reaction, and there must be some support at B. That is meaning of it. So like this, you have to develop a free body diagram of or load and beam and the load distribution diagram, and then what you can go for is with earlier numerical what we have done for calculations of bending moment at different sections, and then you can draw that bending moment diagram. So bending moment can be calculated as usual, and BMD will be as shown in this particular figure. So this much was the discussion for this lecture. I am concluding this lecture. Thank you all.